Hi, I'm A De Franco, a fellow of the Fieri ITN, and I'm reading for a PhD in astrophysics at the University of Oxford. Today, I will briefly introduce in this video my research. There are extremely violent processes in the universe which can emit the highest energy of photons, the so-called gamma rays. Among them, supernovae, gigantic black holes swallowing matter around them and emitting super-relativistic jets of particles. Or the most luminous phenomenon in the universe, the gamma ray bursts, which in just few seconds can release the same energy that a star like our Sun would emit in its entire lifetime, which is about 10 billion years. So how much do we know about these objects? Let's have a look to the sky with very high energy gamma rays eyes. In 1996, only 3 sources in the sky were known to be emitting gamma rays. In 2003, this number increased to 20, but we had to wait until 2014 to have catalogs of more than 150 sources. The rapid increase of the field is suggesting that we are just looking at the tip of the iceberg, and scientists need the facilities of new generation to observe the universe. The Cherenkov Telescope Array, CTA, is a new observatory that will see the sky in the photon energy band between 100 GeV up to 300 TeV, with an order of magnitude increase in flux sensitivity, energy and angular resolution over the state-of-the-art experiments. To do so, more than 100 telescopes will be deployed from next year among 2 different sites in the northern and southern hemisphere. Let's now have a look on how ground-based experiments like CTA can detect very high-energy gamma rays. A gamma ray entering the atmosphere interacts at a high altitude, about 20 km above sea level, and produce an electron-positron pair. Those will travel until they scatter, lose part of their energy, and emit a gamma ray of lower energy than the primary one. These 2 processes repeat in a cascade, multiplying the number of particles until their energy is not sufficient to proceed the reactions. The shower of particles cascades down to the ground for about 15 km, at a speed slightly faster than the speed of light in the atmosphere, emitting Cherenkov radiation and creating a flash of light that illuminates an area of few hundreds meters on the ground and lasts only few nanoseconds. Placing a telescope anywhere in this light pool with a camera sensitive to very low illumination levels, few photons per pixel, and fast enough, nanosecond precision, would permit to imagine the showers and with high level of complexity analysis reconstruct the energy and arrival direction of the primary gamma ray. 2 telescopes looking at the same event can improve the reconstruction with stereoscopic view. But this requires nanosecond synchronization between telescopes hundreds of meters apart. Now let me give you more details on my research, which is focused in addressing all these very challenging requirements. I helped developing, prototyping and testing, in collaboration with a very international team, a camera to be operated of the Gamma Ray Cherenkov Telescope, GZT, a design proposed for CTA. If we use a dual mirror telescope, we can reduce the size of the camera focal plane down to about half meter in diameter, and use multi-anode photomultiplier tiles, which consist of a matrix of 8 by 8 PMTs for a total of 64 pixels. Our camera is composed by 32 of these modules for a total of 2048 pixels. The signal from each pixel has to be digitized with a precision of 1 nanoseconds. Therefore, the group developed a custom-made front electronics module able to do so. In addition, we have to fight with a very high rate of noise, 20 million photons hitting each pixel in a second, against a very modest rate of interesting events happening, 600 times a second, and lasting only few nanoseconds each. To solve this problem, we had to develop algorithm and electronics able to tackle the problem. The front-end module generates a first-level trigger on the threshold discrimination of the sum signal of 4 neighboring pixels. A backplane collects the 512 first-level trigger lines and performs neighbor coincidence at 1 nanosecond level in one of the most powerful FPGA available, which send a camera without trigger to the front end that will stream the data to a data acquisition board. The camera is kept synced with all other telescopes to the nanosecond, thanks to a white rabbit switch residing on the DAC board. The choice we've made showed to be successful in December 2015 in Paris, where the prototype recorded the first light from cosmic ray-induced showers. It was the first time a dual-mirror Cherenkov telescope proved to work, even if the light pollution next to the cities was really high.
In the framework of the inferior ITN networks, I'm exploring collaboration on development of electronics and sensors used by other experiments in particle physics and medical physics, which have similar common needs. Especially silicon photomultiplier, which shows a series of advantages over multi-anode photomultipliers, but most noticeably is the tolerance to very bright light. Therefore, we could afford to observe during full moon night with CTA, and this would increase a lot the duty cycle of CTA.